Good morning, everyone. Welcome back. Thank you for joining us. We are back twice a day. Scott survived girls' camp. Cookie, we'll call him Cookie.
Yeah,
We're going to try and get you through this Monday morning. I'm Steve.
and I'm Scott.
Together, we are Backyard Musings, the Science and Technology channel.
Yep, and we're talking about this is a topic we haven't talked about for a long time, but it seemed like we were talking about it on a pretty regular basis, and that is quantum computing.
Yeah, it's been a while.
Am I pronouncing that right? Magnons?
Magnons, yeah.
Okay, so here we go.
For decades, magnons have shown enormous promise for quantum technologies, but one critical limitation has kept them from practical use. They disappear almost as soon as they form. Yeah, that could be a problem, Physicists at the University of Vienna have discovered magnons with lifespans 100 times longer than previously measured. That's still a short lifespan. Would you like to know more?
Now, an international team of physicists led by Andrei Schumack at the University of Vienna has increased magnon lifetimes by nearly 2 orders of magnitude, from just a few hundred nanoseconds to as long as 18 microseconds. So, Steve, you got to tell us, what's the difference between a nanosecond and a microsecond?
A nanosecond is not even a fraction of a blink of your eye, and
Okay.
a microsecond is a blink of your eye.
Oh, okay. So quite a bit then.
Yeah,
Okay.
well, yeah, but it's still in microseconds. It's here and gone quickly. The researchers also discovered that this limit is not set by fundamental physics, but largely by material quality, pointing to a clear path toward even longer-lived magnons. The breakthrough could ultimately help enable highly compact quantum computers, potentially no larger than a 1-cent coin. The findings were published in Science Advances on May 1st, 2026.
Magnets move through magnetic solids as small waves in magnetization, similar to the ripples spreading across water after a stone is dropped into a pond. Physics. Unlike photons, which can move through empty space or optical fibers, magnons travel inside solid magnetic materials.
Okay, so like battery material, solid state stuff.
Okay.
Their wavelengths can shrink to the nanometer scale, meaning magnonic circuits could, in principle, be built on chips no larger than those already used in today's smartphones. Because a magnon is an excitation inside a solid, it also naturally interacts with many other fundamental quasi-particles, including phonons and photons. This makes magnons promising building blocks for hybrid quantum systems and quantum metrology.
The central challenge has been their short lifetime. This is the span during which magnons can reliably carry quantum information, and previous experiments reached only a few hundred nanoseconds at best. That was far too brief for practical quantum computation. The Vienna-led group has now reported a major step forward, measuring magnon lifetimes of up to 18 microseconds, almost 100 times longer than any previously observed value. At that time scale, magnons become more than brief signals. They begin to resemble long-lived, dependable carriers of quantum information, similar in function to the superconducting qubits used in many leading quantum processors today.
The breakthrough came from combining two approaches. First, the group used short wavelength magnons rather than conventional uniform type. These short wavelength magnons are naturally less affected by defects on the crystal surface, the same defects that had shortened magnon lifetimes in earlier experiments. Second, ultra-pure spheres of yttrium iron garnet, YIG, were cooled in a mixed-phase cryostat to just 30 millikelvin, only a tiny fraction of a degree above absolute zero. At such extreme temperatures, the thermal processes that normally destroy magnons are effectively frozen out.
The most important finding was that the remaining limit on magnon lifetime does not come from a basic law of nature. Instead, it comes from tiny trace impurities in the crystal. 3 spheres with different levels of purity were tested, and the pattern was clear. Pure material allowed magnons to survive longer. Even the least pure sample exceeded all earlier records. That means the next advances may depend on better materials rather than new physics, leaving a clear path for future progress.
With lifetimes reaching 18 microseconds, magnons could shift from lossy intermediate links into durable quantum memories and low-loss communication channels on a chip. They may be able to connect hundreds of qubits along one shared pathway, creating a long-sought quantum bus that could provide a missing piece for scalable quantum computers.
Because magnons exist in a solid and can couple to many different quantum systems, they could also act as universal translators in hybrid quantum architectures, helping technologies communicate that otherwise would not easily connect. So, I don't know. This is, I mean, they're definitely moving in the right direction, right? But, I mean, and they're
They got to
probably
get it more than 18 microseconds. That's
yeah, but they're probably
not even
giddy
blink the eye.
about that, right? Just, I mean, that's a big leap, quantum leap, right? But
Well, I
not,
guess that could be the difference between first place and second place in a track meet.
yeah.
That
But, I mean,
no,
right now, that's as fast as they go, right? So hopefully they're still working, and maybe someday it'll be 18 seconds instead of 18 microseconds. So
yeah.
very cool. Okay.
All right, folks. Thanks for joining us. We'll catch you in the afternoon.
Take care, everyone. Thanks.